Hello, my name's Chris Garvey, and I'm going to continue my series of webinars on the small angle scattering and introduction. So, welcome to the fifth lecture. In this lecture, we're going to be talking about data analysis, how to get to structural information from the scattering curve. In the first case, I'll be looking at some very specific structural analysis. That is the indexing of liquid crystalline phases. This is very specific, and I'll take a few slides to do that, but quite useful. After that, I'll be looking at more diffuse scattering. So I'll talk about limiting laws of scattering, which I've already talked about, the Poirot law and the Guinier law. I'll talk about an integral scattering law, which basically describes the area under the curves and relates that to the composition of the sample. I'll talk very briefly about indirect Fourier transforms of scattering data. So if one thinks of the scattering curve as a Fourier transform of the real space model, this is a further Fourier transform which gives us some idea of the size and the shape of particles. And finally, I'll talk about the most popular way of dealing with small angle scattering data, that is data modeling. So in the first part of this lecture, I'm going to talk about diffraction from soft matter systems. And I've given really quite a nice review of this with application to membrane lipids. So just to revisit some basic theory in the context of lamellar diffraction, we have a periodic structure, which is bilayers stacked upon one each other. And because of the phase shift induced by the periodic structuring, we see a scattering pattern which is made up of well-defined peaks with a well-defined spacing between them. The distance between the peaks is indicative of the bilayer spacing. So if we think a little bit further along, each of these peaks is the same distance apart from each other, and each represents an integral number of the Q spacing. So if we do a linear regression of Q max, we can easily calculate the periodic spacing from the slope. A much more complicated arrangement of lipid molecules in the so-called hexagonal phase. It's essentially a two-dimensional array of hexagonally arranged cylinders projecting out of the page. And again, there's a periodic structure with several characteristic length scales. And these lead to constructive interferences, which give characteristic peaks, which are indicative of the spacings which make up the arrangement of the hexagonal phase. Now, we'll be dealing with these two cases in the practical sessions. These arrangements can get really quite complicated. This is a slide which shows some cubic phases, which are bicontinuous networks of water and some other phase, or air in the case of the butterfly wings. Let's just look at the butterfly wings in a bit more detail. And so the butterfly wings consist of a single gyroid network of chitin, and this is actually what gives these kind of butterflies their color. It's so-called structural color. So the periodic spacing causes an interference phenomena with light, which gives these butterflies their green color. And of course, you can put these materials, these butterfly wings, in this case, a synchrotron Sachs beamline, and get the d-spacings or the periodic spacings of the lattice in the butterfly wing from the scattering pattern. That's down in the bottom. But the main subject of today's talk is much less interesting scattering patterns. They're much more diffuse. There may be something like a peak inside, but of course it's badly defined. Usually they're just simple decays characterized by different slopes. We tend to analyze these curves in quite particular ways. The first, which I'll go into an example in a little bit more depth, is just looking at the slope of the log intensity versus log Q plot. And this can give some ideas of the structures or the fractal dimensions of the structures that we're looking at. There's also some model-dependent limiting laws which we've already talked about. I'll just re-mention them briefly. The Pollard invariant, which predicts the total scattered intensity. The Gounier law, which is good for getting the sizes of objects. And the Pollard law, which is quite useful for getting the size, but also the composition. And I'll show an example of this, of phases. I'll talk about briefly the transform methods of getting structure from scattering curves, and this involves a further Fourier transform of the scattering data. But I'll focus most of what I talk about today on modelling, because this is the most popular way of getting structural information from scattering curves, and in terms of publications, it's the one that people believe the most. So when you're dealing with skeptical reviewers, it's possibly good to have a model in. So the simplest way of looking at a scattering curve to start with, and you may be even tempted to do this with your data, is just to look at the power law that the log intensity versus log Q obeys. Now these can just be identified in terms of simple shapes, and we showed an example of this with vesicles where the different Q regimes gave different slopes. But here's sort of a compilation of some typical power laws and what they're associated with. There's some reviews at the bottom, but I thought it'd be much more useful to go into a fairly detailed example where this approach has been really quite powerful in understanding a scattering curve over an extended Q range. So the example here is from my colleague Francois Bouy of the neutron scattering laboratory in Saclay, France. What he has is a solution of lysozyme in a polyelectrolyte polystyrene sulfonate, and the solutions are turbid and they don't flow at all. Now, although this is a multi-phase scattering problem, that the solution consists of protein, polyelectrolyte and water, what's being done in this case is the match of water and the polystyrene sulfonate means that one only sees how the protein is behaving in solution. So what I've done here is I've just drawn the form factor of the protein, and you can see that it just displays a Gounier radius, whereas the actual scattering exhibits a peak due to the structure factor. And so the proteins are aggregated together, they're quite close together. If one goes to a lower Q, one sees a Q to the -4 dependence, and this is due to aggregates of the lysine molecules held together by the polystyrene sulfonate. The Q to the -4 dependence is not actually the aggregates themselves, but the interface between the aggregates and the surrounding solution. And indeed, one goes to lower Q, one starts to see first of all the overall aggregate, the curvature, and then these smaller aggregates formed into fractally scaled aggregates made of the unitary aggregates. By contrast, here's a TEM picture of a freeze fracture from the same material, and it's nowhere near as informative, and certainly the measurement takes a lot more care than the SANS measurement. So I'll talk briefly about the indirect Fourier transform methods and the software which are used to do this. It's basically a transformation of the scattering curve with a Fourier transform. There's some particular difficulties in transforming small angle scattering data in this way. The pair distribution function, or the pair distance distribution function, or PDDF, is good for giving an estimate of particle shape and size from small angle scattering data. It's completely model independent. Most data processing suites these days have some implementation of this. Some examples are ATSAS, which is used quite often for solution scattering for proteins, and the more generally used SASView. There's a web-based application, and GIFT has been used for a very long time. There's a very nice presentation on the web about the GIFT, and that explains it really quite well. Here's an example of a scattering curve from a sphere, and it's been transformed into a paired distance distribution function, and the shape of this curve helps you identify that it's a sphere. Here are some more complicated structures and the paired distance distribution function for each of them obtained from small angle scattering. And the take-home message from this here is that it's able to identify characteristic distances. So for these objects where there's some very characteristic distances, highly geometric, it's an excellent way of determining what the structure is. But if you're more interested in it, there's the reference that I gave you. The Guinier law, which we've brought in before, is an excellent way of measuring or estimating the size of objects at low Q. You can also use it to estimate the volume of particles if you know how many particles there are and their contrast. The main assumptions of the Guinier law is that it's a low Q extrapolation, so the Q is much smaller than 1 over the radius of gyration. It's a dilute solution scattering law, so we assume that all the scattering is from the form factor of the particles. It also assumes that the scattering bodies are isotropically distributed. And as I said before, it's really quite useful for estimating the size of particles. The Poirot law is a high Q limiting law. So it talks about the limit at high Q of the scattered intensity. So when one considers a two-phase system as shown in the right-hand side, if the scattering vector is much larger than the curvature of the system, one sees effectively a flat surface. Here I've given an example of scattering from 3 diatoms, which are phytoplankton, and clearly from the electron micrographs at some length scales they're curved. But if you look at the scattering curves over a large range of Q, there's this -4 slope that's given by the red line. And we may use this limiting intensity to estimate the surface area per unit volume of the sample. And so what I've given there in the table are surface areas estimated from the Poirot region and surface areas which have been measured directly from the BET absorption isotherm for nitrogen. The numbers agree quite well. Another useful property of a scattering curve is the invariant, which is just the integral of the curve. Now, it's easy enough to integrate a curve numerically, and if one can extrapolate well to low Q using the Guinier law, and to high Q using the Poirot law, then one can use this really quite powerfully. In the example in the reference at the bottom, we just use this to follow the growth of silicon nanoparticles in solution. And we were able to get some real insights in the kinetics of the growth of these silicon nanoparticles. In the remainder of this talk, I'm going to focus on data modeling. So in this approach, one calculates the scattering based on a mathematical model and use the parameters in that model and compare what you can calculate to the actual measured scattering to get an estimate of the structure. It's important to realise that this is not a standalone technique for determining structure, i.e. that the model fits doesn't guarantee you have a unique structural solution. And in the approach, it's very important to minimise the number and the range of free parameters. And a good example of this is not to leave the polydispersity and the shape as free parameters. It's best used for sound systems that are well understood, which is to say you can't search through all parameter space to get a unique structural model. And it's really quite powerful when you're examining global structural changes, so you have some other knowledge of the system. So I'll give you a brief overview of the data modeling packages that are available. They're all pretty much the same. They just implement the approach slightly differently. There's a bit of a list there in the first link if you want to go and have a look. There's rather a lot of modeling macros available for Ego Pro, and we also use this for data reduction, so it's quite useful. One of the more common packages is SAS View, which is free. Ego Pro does cost money. SAS View has a nice user-friendly GUI. It has a large range of models, and you can also write models if you're that way inclined. It can cope with both 1D and 2D data sets. It includes size distributions or polydispersity, and it also has some nice tools for calculating integral structural parameters. There's a link there for the program, and I'll give a bit of an overview in subsequent overheads. And another nice and equally effective free package is SASFit. It doesn't have quite the user support as SAS View. It's also free. It has a nice GUI. One of its real powerful attributes is its ability to do global fitting of contrast series. It handles a large range of models and 1D data sets, and it also handles size distributions or polydispersity. So here's an example of some modeling calculations from a sphere, and I've superimposed the limiting laws on there as well, so you can see the same information is there. But I guess what it does do is allows you to integrate all this information into the one curve. Here's an example also of modeling. In this case, it's a cylinder or a rod. And again, the same caveats apply, that you can still identify all the attributes one would expect from a cylinder, but what it allows you to do is to give the scattering over the complete Q range and integrate all this information. And as a final word on calculating scattering, I have this interesting example where this is just pores of different sizes in a matrix, and in this case they've assumed the pores are spherical, and they've just fitted a size distribution over the pores, and this works quite effectively. So what I'll try to give you now are some general considerations in terms of fitting. How to constrain parameters and how to use the software. In this case, it's SAS View. We will be doing some actual examples of fitting in the practical sessions, but at this stage, I just want you to think about the buttons that you press and how you get the answer. So I'll give you a link. There's a link on the web page for the course on how to download it. But if you download it, the left-hand side will give you a view of the GUI as it opens. And what I'd like you to focus on is the fit panel. So to focus on the model parameters a little bit further, the scale is just a scaling factor that moves the curve up and down. Usually we just fix this as 1 because we know that we have a good idea about the rest of the parameters, but it can be useful. The background, we know this exactly for neutrons, and I'll talk about that in the practical session. The SLD is absolutely constrainable. Usually you know it quite well, or it's been measured. The SLD of the solvent is something you know exactly. The volume fraction, you can also calculate from the concentration, particularly if you know the molar volume of the molecule. For the radius, we tend to constrain that by DLS, and that's a sample preparation issue. And for the thickness, well, because they're lipid vesicles, the thickness is quite highly constrained, and this also becomes an important parameter when you look at the sample quality. We'll have a nice example of that in the practical session. So in the next lecture, we'll just wrap things up. There's a few pieces of information I think you're missing, and we'll also talk about the complementarity of other experimental techniques. And finally, we'll look at those large-scale facilities which are developing in Sweden at the moment.